Tonight, as you lie back after a long day and let the room go dim, I want to tell you something simple and a little unsettling. In the last few years, the James Webb Space Telescope has found galaxies as massive as the Milky Way, when the universe was only about 300 to 500 million years old, less than 4% of its current age. It has seen black holes already weighing hundreds of millions of suns at a time when, according to our best equations, there shouldn't have been enough time to grow them. It has found smooth, orderly structures where there should have been chaos. None of this should be possible. For almost 100 years, the Big Bang Theory has been our best story about how everything began. A hot, dense beginning, space expanding, matter cooling, tiny fluctuations in the early universe slowly pulling gas together over hundreds of millions, then billions of years, until the first stars, the first galaxies, and eventually us. In that story, the early universe is supposed to be simple. Small clumps of matter, messy baby galaxies, no heavy elements yet, no fully formed disks, no giant black holes sitting at the centers of things. But that is not what James Webb is seeing. Instead, when Webb looks back to what we thought was cosmic dawn, it finds something that looks more like midday. It sees galaxies that seem fully built, stars that have already lived and died and filled space with metals, and black holes that look like skyscrapers in a universe where we were expecting tents. Tonight, we're going to follow that tension, not in a frantic way, not with clickbait panic, but slowly, calmly, the way you might walk out onto your porch at night and look up at the sky, just to see what's changed. We'll talk about the galaxies that shouldn't exist, the stars that look too old for a young universe, the black holes that appear fully grown when the universe was barely out of childhood. And we'll talk about what all of this does to the story of the Big Bang, not to destroy it, but to show you where the cracks are and why those cracks are so interesting. Because if you clicked on this video, you probably felt that tug in the title, the James Webb Discovery that Breaks the Big Bang Theory. Maybe a part of you wondered if everything you learned in school was wrong. Maybe another part of you just thought, I want to know what's going on up there. You're in the right place. In the next hour, I'm not going to ask you to pick a side or memorize equations. I'm not going to drown you in jargon. What I am going to do is take you by the hand, sit with you in the dark, and walk through the evidence that has cosmologists rethinking the beginning of the universe. We'll meet Webb itself, the cold, golden eye floating a million miles from Earth. We'll dive into the data, the impossible galaxies, the smooth structures, the overachieving black holes. We'll revisit the core ideas of the Big Bang, the role of dark matter and inflation, and the models that might extend or replace them. And through it all, we'll keep the pace slow enough that you can relax, let the words wash over you, and maybe drift a little as your mind walks around these questions. By the end, you won't just have a headline in your head. You'll understand why some astronomers say the universe seems to have built things too early, too fast, and too well. You'll see why redshift, the ruler we use to measure cosmic time, is under pressure. You'll see why the phrase cosmic dawn might be misleading, and why some people suspect we've been staring at the middle of a much longer story. And if that sounds like a lot for this time of night, don't worry. You don't have to solve it. You don't have to fix the Big Bang. You don't even have to stay awake for all of it. All you have to do is listen. Let your shoulders sink into the bed or the chair. Let your eyes soften. Let the day slide behind you. Above you, somewhere far beyond the ceiling and the clouds, a silent telescope is still collecting ancient light, one photon at a time. That light is what started this crack in the story. Tonight, we're going to follow it. Before we talk about the galaxies that broke the Big Bang timeline, we need to talk about the machine that found them. Because the James Webb Space Telescope isn't just a telescope. It's the most sensitive time machine humanity has ever built. One capable of detecting a single ancient photon that has been traveling toward us for more than 13 billion years. Webb sits 1 million miles from Earth at a gravitational pocket called L2, a place so stable that a spacecraft can hover there with almost no fuel. Out at L2, the Sun, Earth, and Moon all sit on the same side, leaving Webb in permanent darkness. Darkness is vital. Not poetic darkness, literal darkness. Even a whisper of warmth would destroy its vision. So, Webb hides behind a sun shield the size of a tennis court. 5 silver layers stretched tight, like the wings of a giant mechanical moth. Those layers keep the telescope colder than almost anything in nature. 200, 330, 388 degrees. At that temperature, Webb is so sensitive that the heat from a human body would overwhelm its instruments instantly. If an astronaut stood within a mile of it, Webb would be blinded. That's how quiet the telescope must remain to hear the oldest light in the universe. Then there's the mirror, the part everyone recognizes. 18 gold-coated segments forming a 6.5-meter hexagon, polished with such precision that if each segment were the size of the United States, their imperfections would be smaller than the thickness of a dollar bill. And that golden eye is tuned not to visible light, but to infrared. Here's why that matters. The farther light travels, the more the expansion of the universe stretches it, pulling it from blue to red and eventually into the infrared, where human eyes and most telescopes are blind. That means the earliest galaxies are invisible to anything except a machine built specifically to see those stretched out wavelengths. This is the reason Webb exists. Hubble showed us beauty. Webb shows us history. When Webb looks deep into space, it isn't just seeing distant objects. It's seeing objects as they were billions of years ago. Distance equals time. And Webb can look back 13.5 billion years, within a heartbeat of the universe's beginning. That capability shaped its mission. Map the first stars. Observe the first galaxies. Measure the earliest black holes. Test the Big Bang timeline with actual data, not models. NASA's expectation was simple. Webb would confirm the story we already had. That didn't happen. Because from the very first deep field, before the mission even settled into full routine, Webb detected objects so bright, so massive, so evolved, that astronomers thought they were calibration errors. One scientist later admitted, "We were ready to blame everything: dust, noise, instrument drift, anything except the universe." But the data kept repeating itself. Take a moment and picture this: a golden eye, floating in a cold, silent orbit a million miles away, perfectly still, perfectly dark, collecting photons that left their galaxies before Earth existed, and assembling them into images so sharp they challenge a century of cosmology. This is why Webb matters. Not because it's beautiful, not because it's expensive, but because it can see things no instrument in history has ever seen. It was built to confirm the Big Bang timeline, but its first discoveries began to bend that timeline instead. It's powerful enough to break the story. And that brings us to the first moment scientists realized something was wrong. The moment when a baby universe revealed fully grown galaxies. And the first surprise came fast, faster than anyone expected. When the very first deep field images from Webb finished downloading, the room where the scientists were gathered went strangely quiet. Not the excited, buzzing kind of quiet, but the kind where everyone is holding their breath at the same time without realizing it. On the giant monitor, thousands of tiny red dots filled the frame. At first glance, it looked like the same kind of deep field we'd seen before. Faint galaxies, scattered stars, the soft glow of the early universe. But Webb's images are sharper. So the scientists began zooming in. One dot, then another, then another. These were supposed to be baby galaxies, the cosmic equivalent of toddlers, misshapen, lumpy, barely held together by gravity. That's what the models had predicted for decades. But as they zoomed closer, the room grew even quieter. Because these galaxies didn't look like babies at all. They had disks, smooth and circular. They had bulges, dense centers full of stars. Some even showed hints of ordered rotation, a kind of cosmic choreography that takes hundreds of millions of years to develop. One astronomer whispered what everyone else was thinking. These look like spiral prototypes. And in a universe this young, they shouldn't exist. Not even close. It was the kind of discovery that makes you blink and look again, as if your eyes are tricking you. To help you feel what the scientists felt in that moment, imagine this. You walk into a kindergarten classroom, and instead of children, you find a room full of middle-aged men in suits, talking about mortgages. That's the level of wrongness we're dealing with. Because at this point in cosmic history, redshift 10 to 14, less than 500 million years after the Big Bang, the universe was supposed to be too chaotic, too hot, too fast expanding to build anything this adult. To make a big, smooth galaxy, you need multiple generations of stars, the debris from supernovae, time for gas to cool, time for orbits to settle, and time, above all, for gravity to sculpt order from chaos. But the early universe didn't have that kind of time, not by a long shot. Yet here were galaxies, too bright, meaning too many stars, too massive, meaning too much matter had collapsed too quickly, too smooth, meaning their structures were already well organized, and too early, showing up just a few 100 million years after the Big Bang. It wasn't one odd galaxy. It wasn't two. It was many. They kept showing up in every deep field Webb produced, as if the universe were saying, "Look more closely. Your timeline doesn't fit what actually happened. Take a moment here. Slow down with me. Imagine opening the universe's baby photo album and seeing a fully grown adult staring back. That's why this matters. Because if galaxies matured this quickly, then either our understanding of early star formation is incomplete, or our timeline is off, or something about the early universe moved faster, grew faster, or behaved differently than we thought. You don't need a PhD to sense the problem. You can feel it intuitively. Something is deeply off with the early universe. Garth Illingworth, one of the world's leading experts on galaxy formation, said it best. We're seeing too much too soon. And he wasn't exaggerating, because this anomaly, this impossible level of galactic maturity, was just the beginning. Other surprises were waiting. Stranger ones, bigger ones. And to understand why these galaxies are impossible, we have to revisit the story we've believed for nearly a century. Before we break a theory, let's understand why it survived for so long. Because for nearly a century, the Big Bang wasn't just a scientific idea. It was one of the most successful, elegant, and beautifully consistent stories humans ever told about where everything came from. And before Webb arrived, it made perfect sense. Let's slow down, take a breath, and walk gently through that story. The Big Bang was never meant to be imagined as an explosion. Not a fireball, not a bomb, not a blast in empty space. Instead, it was the moment space itself began expanding, stretching out from a state that was unimaginably hot, unimaginably dense, and unbelievably small. Not a point in space, but a point of space. And that expanding fabric carried matter, energy, and light outward with it, cooling as it grew. In the earliest moments, everything was a soup of particles. No stars, no galaxies, not even atoms yet. Just pure, glowing pressure. Over time, as the universe kept expanding and cooling, it became transparent. Light could finally travel freely. And that first free light is still here. We call it the cosmic microwave background, or CMB, a soft afterglow bathing the universe in a faint uniform warmth. Imagine walking into a room hours after a fire has burned out and still feeling heat on the walls. That is the CMB, the leftover warmth from the universe's first 380,000 years. This was one of the Big Bang's strongest pieces of evidence. The others were equally powerful. First, the redshift discovered by Edwin Hubble. Galaxies drifting away from us, their light stretched like the deepening pitch of a truck driving off into the distance. Space is expanding. The universe is growing. Backward in time, everything must have been closer together. Second, the precise ratios of hydrogen, helium, and lithium, the universe's light elements. They match perfectly with what we'd expect from a hot, dense beginning. These elements are chemical fingerprints pressed into the cosmos during its first 3 minutes. Third, the CMB itself, smooth, even astonishingly uniform. A baby photo of the universe with details so fine that scientists could measure tiny ripples of early matter, the seeds of all future galaxies. Taken together, these 3 pillars made the Big Bang feel complete. But even the strongest stories have cracks. Astronomers eventually noticed 3 big problems. The kind that don't break the Big Bang, but do make it feel incomplete. The horizon problem. How could parts of the universe so far apart be almost the exact same temperature when they never had time to exchange heat? The flatness problem. Why is the geometry of the universe so precisely balanced, neither curved inward nor outward, when even tiny changes early on should have snowballed into something very different? The monopole problem. Why don't we see the heavy exotic particles predicted by early high-temperature physics? To fix these issues, physicists introduced a brilliant idea: cosmic inflation. A moment just a fraction of a second after the universe began, when space expanded faster than the speed of light. Not matter, not energy, just the fabric of space itself, ballooning outward at impossible speed. Inflation stretched out any irregularities. It smoothed the universe. It explained the uniform temperature. It solved the horizon problem, the flatness problem, and the missing monopole problem in one stroke. It was elegant. It was powerful. And for decades, it worked. It felt complete. Scientists grew comfortable with the idea that the universe started simple. A hot, dense, uniform soup that gradually grew more complex as it cooled. Simple, structured galaxies, stars, planets, us. That was the rule. That was the timeline. And everything we observed supported it. Until Webb looked deeper. Because inflation and the Big Bang model both require that the early universe begin in a simple state. Messy, chaotic, disorganized, and primitive. But Webb didn't see simplicity. It saw complexity. Right at the beginning. Smooth disks, massive galaxies, ordered rotation. A universe acting far older than it should have been. Inflation was meant to fix everything. Until Webb looked closer. And that's where our story begins to turn. Where a theory that once made perfect sense meets data that refuses to fit. The Big Bang wasn't wrong. It was simply incomplete. But hints of trouble were already hiding in the data long before Webb. Long before Webb opened its golden eye. Another telescope had already whispered the first warnings. If you were alive when the Hubble Deep Field was released, or even if you just remember seeing it for the first time, you'll know the feeling. A tiny square of sky, so dark, so empty, you'd expect nothing at all, just blackness. But Hubble pointed at that emptiness for days, collecting every photon that wandered in. And when the final image appeared, humanity gasped. Because almost every tiny speck, every dot, every smudge, every flicker was a galaxy. Not a star, not a planet, a galaxy. Thousands of them. In a patch of sky, the size of a grain of sand held at arm's length. It was the first moment many people realized how profoundly crowded the universe really is. A moment that made us feel small, but in the most beautiful way. Yet hidden inside that masterpiece were a few objects that didn't behave the way the textbooks said they should. Hubble saw galaxies that were too bright, too smooth, too mature. For a universe that young. One of them, GNZ11, became famous. Hubble measured it as one of the most distant galaxies ever seen, bright enough and structured enough to make astronomers raise an eyebrow. But back then, the tools weren't sensitive enough to be sure of anything. Maybe it was noise. Maybe it was a quirk of the data. Maybe the redshift was misinterpreted. Maybe Hubble had simply reached its limit. That's how science worked at the time. If something didn't fit, you checked the instrument first, not the universe. There were whispers, of course. A few astronomers asked quietly, "What if these aren't errors? What if these galaxies are trying to tell us something deeper?" But the community didn't chase those questions too far. Not because they were ignoring the truth, but because the standard model explained almost everything else so well. The light element ratios worked. The cosmic microwave background worked. Expansion worked. So the outliers were placed in a drawer labeled, probably instrument noise. And the drawer stayed closed. Until Webb opened it. Because Webb didn't just have better mirrors, it had infrared vision, deeper sensitivity, and the ability to see farther back than any telescope before it. It looked at the same kinds of regions Hubble once studied, but deeper, sharper. With clarity Hubble was never designed to reach, and the result was unavoidable. Those strange galaxies, they weren't mistakes. They were real structures, real mass, real maturity in a universe far too young to host them. For years, those anomalies had been like a whisper at the edge of our hearing, barely visible, easy to explain away. Webb didn't invent the anomaly, it simply turned up the volume. And suddenly, the universe's quiet warning became impossible to ignore. The universe was already trying to tell us something. We just didn't have the ears to hear it clearly. With Webb, those hints turned into a pattern that simply didn't fit the old timeline. How fast can you build a city from scratch? Not a village, not a handful of wooden houses, a real city, skyscrapers, highways, power grids, millions of people. 6 months? Impossible. Now zoom out with me, far beyond Earth, beyond our cities, beyond every skyline we've ever constructed. Because the universe faced a similar challenge. How fast can you build a galaxy from scratch? You start with dark matter halos, invisible scaffolding forming in the early universe. Gas falls into those halos, cools, condenses, forms the first generation of stars. Those stars live, burn their fuel, explode. Their explosions scatter heavier elements, metals, into space. Gas enriched with metals cools faster, forming second-generation stars. Then third, then fourth. Cycle after cycle, slow, cumulative, step by step. And only after many hundreds of millions of years do you get something resembling a stable, ordered galaxy. That's the picture painted by LCDM, the standard model of cosmology. It's clean, it's logical, it makes sense. But then Webb looked back to redshift 10, 12, 13, and the universe did something it wasn't supposed to do. It showed us galaxies that had no right to be there. Some had stellar masses rivaling the Milky Way, meaning hundreds of billions of stars, in a universe only 300 to 500 million years old. That's not just impressive, that's absurd. Because to build a galaxy that large, you need multiple cycles of star birth and death time to create metals. Time to recycle those metals. Time for disks to settle. Time for gravity to organize the chaos. But the early universe didn't have that time. It wasn't old enough to have finished even one full generation of star formation in some models. And yet Webb was finding galaxies that looked like they'd gone through dozens. And they weren't rare. They showed up across multiple deep fields, each one a cosmic skyscraper city appearing in an era when the universe should have only had the raw materials for tents. One astronomer looked at the early data and said it plainly. These objects are just too massive to have formed so quickly. If they're real, our models are in serious tension with reality. Joel Leja, Penn State. Think about that. In the time it should take to build a small cosmic village, the universe somehow built entire cities of stars. Let that sink in for a moment. A universe barely out of its cosmic crib, hosting galaxies bright enough to challenge everything we thought we understood about structure formation. Some had star formation rates so high they bordered on the theoretical maximum, as if these galaxies were burning through gas with frantic urgency. Others had morphology, disks, bulges that should have required long periods of stability. It's like expecting a quiet rural town and instead finding Manhattan. So what do you do with something like that? Astronomers branched into 3 possible explanations, none of them comfortable. First, maybe we underestimated how fast stars can form in the early universe. Perhaps the first galaxies were far more efficient than anything we see today. Second, maybe the physics of gas collapse under early universe conditions is very different. Maybe colder, denser, more turbulent, more efficient. Third, maybe our ruler is wrong. Our measurement of distance, our measurement of time, our reliance on redshift as the clock of the cosmos. Because when you look at an object's redshift, you're not just measuring color, you're measuring age. Redder light, older light. That has always been the rule. And so far, it has worked beautifully. But these galaxies, these massive, mature skyscraper cities of stars, are starting to pull at that assumption. And every tension we've seen so far leads us one step closer to the heart of the problem. Because all of this, the mass, the brightness, the size, the maturity, rests on a single idea. That redder means older. And what happens if that assumption isn't as unshakable as we thought? And all of this rests on one crucial assumption, that redder light always means older light. Before we talk about stars that seem older than the universe, we need to slow down, take a breath, and revisit one of the simplest, most powerful ideas in cosmology: redshift, our cosmic ruler, our clock, and maybe, just maybe, a ruler that isn't as straight as we thought. You've heard the effect before, literally. A truck driving past you, a train whistle racing down the tracks, a siren rolling through an intersection. As it approaches, the pitch is high. As it moves away, the pitch drops. A long falling note sliding downward. We've all heard this. It's the Doppler effect. Light works the same way. When an object moves away from us, the pitch of its light stretches. And since color is just the frequency of light, stretching that frequency shifts it toward the red. That shift, that gentle pull from blue to red, is what astronomers call redshift. And for decades, redshift has been our cosmic speedometer. The higher the redshift, the faster an object is receding from us, and the further away it is, and the older the light must be. Simple, efficient, reliable. With one measurement, cosmologists can estimate how far a galaxy is, how fast space is expanding, and how long that galaxy's light has been traveling. Picture a graph. Nothing complicated. Just imagine this. As redshift goes up, distance goes up, and the look-back time, the age of the light, goes up with it. It's a neat relationship, a straight line, a ruler you can trust. Or so we thought. Then Webb arrived. And suddenly, galaxies at extremely high redshift started showing features that didn't belong there. Walls of stars, disks, bulges, metals, black holes, all implying a long, complex history. But redshift told us the opposite. These are from the dawn of time. So something had to give. Either 1. The early universe built galaxies faster than physics should allow. Or 2. The mapping from redshift. Age isn't as simple as we've assumed. Most scientists lean toward the first explanation. It's cleaner, less disruptive, easier to tweak. But the second explanation, That's the one that keeps cosmologists awake at night. Because redshift doesn't just measure motion, it can also be influenced by the path light takes through space. What if ancient light passed through dense early gas fields? What if plasma interactions nudged the wavelength slightly? What if the early fabric of space-time wasn't as uniform as we assume? What if dark matter structures bent and stretched the light in subtle ways? What if the early expansion of the universe wasn't perfectly smooth? These aren't wild ideas. They're simply possibilities. Gentle reminders that the early universe may have operated under conditions that don't match the calm, predictable physics of today. You don't need to follow every theoretical branch. You don't need to track every equation. Just hold on to one simple concept. Our cosmic ruler might be slightly bent, not broken. Just bent enough that when we measure extreme distances, a small distortion becomes a big difference. And when your ruler bends, everything you measure with it bends too. As Adam Rees, Nobel laureate, once said in the context of cosmic measurement tensions, when your measurements don't agree, you're forced to ask if the problem is in the data or in the model you're fitting them to. That's where cosmology sits right now, on the quiet edge between certainty and possibility. Most cosmologists still trust redshift. They should. It's worked beautifully for decades. But trust doesn't mean ignoring the strain Webb is putting on that relationship. Because if redshift is even slightly nonlinear at the highest distances, if early universe conditions nudged ancient photons in subtle ways, then ages shift, distances shift, timelines shift. Not wildly, not chaotically, but enough to change how early truly is. And that brings us to the next twist in our story. Because nothing tests our cosmic timeline harder than stars that look older than the universe should allow. And nothing tests our timeline harder than stars that seem to have lived longer than the universe itself. And nothing tests our timeline harder than stars that seem to have lived longer than the universe allows. To understand why Webb's discovery shook astronomers so deeply, we have to zoom in from galaxies, down to the stars inside them. Because galaxies don't just appear out of nowhere. They're built star by star, through a long, patient cycle of birth, life, death, and rebirth. Let's take that cycle slowly. A cloud of gas collapses. Gravity squeezes it tight. A star ignites, a tiny sun glowing in the dark. It burns. It shines. It lives its life. And when it dies, especially if it's massive, it explodes in a supernova, scattering heavy elements into space. Those elements, carbon, oxygen, iron, all the things that make planets and people possible, mix into the surrounding gas. And from that enriched gas, another generation of stars is born. Generation after generation, layer after layer, a cosmic family tree written in light. Astronomers divide these generations into 3 groups. Population 3, the first stars, made almost entirely of hydrogen and helium. No metals at all. Massive, bright, short-lived. Population 2, stars with a little bit of metals. Not much, but enough to show that earlier stars had already lived and died. Population the Fine, stars rich in metals. Like our Sun, a veteran of many cycles of cosmic recycling. When Webb launched, scientists expected to finally see signs of Population 3, the universe's first true stars, pure and pristine. They should have appeared in the earliest galaxies, shining with a distinct, almost untouched signature. But that's not what Webb found. Instead, Webb looked at early star-forming regions and discovered metals, not tiny traces, not faint hints, but metals at levels suggesting multiple generations of stars had already come and gone. In a universe only a few 100 million years old, Webb was seeing the ashes of stars that had already lived, died, and enriched their surroundings. That shouldn't be possible, because to create those metals, you need stars to form, live their full lives, explode, spread their elements, mix with the gas, form new stars enriched by the old ones. That cycle takes time, a lot of time, far more time than the early universe should have had. Some observations even hint that the first stars might have been incredibly massive, hundreds of times the mass of the sun. They burn hot, die fast, and produce huge amounts of heavy elements. But even then, to reach the levels of enrichment Webb is detecting, the timeline still feels impossibly tight. It's as if the universe ran through several generations of stars in the time it should have taken to form the very first. Here's an image for you, one that fits what astronomers are feeling. It's like walking into a brand new town and finding a graveyard full of old headstones. Somehow, people have lived and died here before the town was even on the map. Close your eyes for a moment and picture that. A newborn universe, barely out of its cosmic crib, already filled with the ashes of stars that had burned, exploded, and passed their elements on to new generations. It's weird, it's beautiful, and it's deeply at odds with the timeline we thought we understood. Volker Braun, one of the leading theorists on the first stars, put it this way: we expected primordial stars. What we're seeing instead are systems that have already been chemically enriched. And that raises a bigger question. If stars in the early universe lived fast and died young, if they enriched their galaxies far earlier than they should have, then something else must also have formed early. Something that is born from the deaths of massive stars. Something darker, heavier, stranger. Black holes. And if stars have already lived and died in this young universe, then what kind of black holes are we about to find waiting there? If galaxies forming too early was the first crack in our cosmic timeline, then black holes appearing too early are where the entire wall begins to crumble. And we need to go slowly here, because black holes, especially supermassive black holes, are a favorite topic for anyone who loves the universe. There's something hypnotic about them. These shadow engines quietly shaping everything around them. Even if you're listening right now just to unwind after a long day, your mind probably perks up a little the moment black holes enter the conversation. So let's start gently. Most galaxies, including our Milky Way, have a supermassive black hole at their center. These monsters weigh anywhere from a few million to a few billion times the mass of our Sun. They anchor galaxies, steer their evolution, ignite quasars, and shine brighter than anything else in the universe when fed enough material. But they don't begin life that big. In the standard model, here's how they grow. A massive star dies. It collapses. A small seed, black hole forms. That seed slowly eats gas, dust, stars. Merging with other black holes over hundreds of millions, even billions of years. And only after all that time does it grow large enough to shape a galaxy. A long process, a gradual one, a timeline measured in cosmic patience. But then Webb looked into the deep past, and the universe did something impossible. It showed us quasars, powered by supermassive black holes, shining at redshift 10 and beyond, only a few 100 million years after the Big Bang. And when astronomers calculated their masses, the room fell silent. 100 million solar masses, 200 million, 300 million, black holes as heavy as the Milky Way's central engine, in a universe young enough to still be glowing with its birth heat. To understand how ridiculous this is, imagine driving through a brand new suburban neighborhood. Fresh pavement, empty lots, no cars, no people. And right in the center of it, there's a completed 120-story skyscraper, fully finished, lights on, functional elevators, coffee shop in the lobby, no cranes, no construction, just instantly there. That's what these early black holes are. To reach those masses, they would need to eat at near the Eddington limit, the maximum stable rate of accretion, continuously, without pause, from the moment the universe began. But the early universe wasn't calm enough for that. It was violent, hot, and expanding fast. Gas fell in, but blew out again. Gravity pulled, but turbulence pushed back. There simply shouldn't have been time for these giants to exist, and yet, there they were. So how do you explain them? Astronomers have broken the possibilities into three main branches, none of them fully comfortable. 1. Direct collapse black holes. Instead of forming from stars, maybe some black holes form directly from enormous clouds of primordial gas collapsing in one catastrophic plunge. This bypasses the stars must die first step, saving precious time. Plausible? Yes, but we haven't confirmed any. 2. Primordial black holes. This idea is more radical. Black holes form not from stars or gas, but from tiny fluctuations in the density of space itself, right after the Big Bang. These wouldn't just be early. They would be older than galaxies, older than stars, older than everything. It's not mainstream, but Webb's discoveries don't rule it out. 3. Faster than expected early growth. Maybe the early universe allowed black holes to feed in ways we don't yet model. Denser gas flows, exotic physics, super Eddington accretion. Maybe the rules were different back then. Take a moment. Slow your breathing. Picture one of these ancient giants, a black hole hundreds of millions of times the mass of our sun, glowing as a quasar at the dawn of time, pouring out more light than entire galaxies in a universe barely old enough to know its own name. Priyamvada Natarajan, a leading black hole theorist, said it clearly. These early black holes are way too massive. Their existence is a tremendous challenge to our theories. The truth is simple. These giants should not exist. Not this early, not this massive, not in a universe still wiping the dust from its eyes. And yet Webb keeps finding them. If supermassive black holes form too fast, then the dark matter halos around them, the structure of galaxies, and the architecture of the early universe must also have evolved too fast. This anomaly is not a crack. It's a fracture. And if the universe built its central engines too early, what does that say about the invisible framework that holds galaxies together? Before we talk about inflation, the biggest patch in modern cosmology. We need to look at something deeper, something quieter, something invisible, but essential. Dark matter. If galaxies are the cities of the cosmos, then dark matter is the steel skeleton inside every skyscraper, the hidden framework that holds everything in place. We never see it directly. We only see what it does. And under the standard LCDM model, it does one thing extremely well. It builds the scaffolding of the universe. Here's the simple story cosmologists have trusted for decades. First, dark matter collapses into halos, big, invisible bubbles of gravity. Gas falls into these halos. The gas cools. Stars form. Stars gather into clusters. Clusters become galaxies. Small galaxies merge to become larger ones. A slow, hierarchical, bottom-up construction process. It is a neat, logical, satisfying picture. And for most of the universe's history, it works beautifully. But Webb is not showing us most of the universe's history. It's showing us the beginning. And the beginning is too clean. Because according to LCDM, the early universe should look like a messy construction site. Tiny dark matter halos, chaotic gas flows, lumpy structures, galaxies too small, too distorted, too young. A universe still laying its first bricks. But that's not what Webb is finding. When Webb looks deep into the past, it sees something that shouldn't be possible. Large, bright, well-formed galaxies sitting inside halos that appear mature, stable, smooth, too smooth. Their disks are not twisted or shredded by mergers. Their shapes are not warped by violent interactions. Even the light they emit suggests calm rotational structure, the kind that should take billions of years to settle. Yet here they are, in a universe only a few 100 million years old, behaving like systems that have existed for 1 billion years or more. It is as if the steel skeleton of the cosmos was finished before the architects even arrived. So how do you explain that? Possibility 1. Dark matter behaves differently than we think. Maybe dark matter isn't the cold, sluggish substance we model it as. Perhaps it's warm dark matter, moving faster, clustering earlier, or self-interacting dark matter, smoothing itself out in ways cold dark matter cannot. Or maybe something about the early universe amplified the way it clumped, accelerating structure formation long before the first stars appeared. None of these ideas break physics, but none of them neatly fit the observations either. Possibility 2. Gravity needs a small modification. This is not mainstream, but it's been whispered for years. Maybe gravity behaves differently at very small accelerations. Maybe frameworks like MOND or relativistic extensions become relevant in the early universe. Not because dark matter doesn't exist, but because gravity might have had a slightly different flavor when the universe was young. We're not committing to this idea, but Webb's data does not rule it out. Possibility 3. The timeline itself is wrong. If redshift is not a perfect mapping to distance and age, even by a little, then these galaxies and halos might not be as young as we think. This doesn't mean the universe is older. It means our measuring stick might be curved, bent, not fatally, just enough to shift the early cosmic schedule. Whatever the explanation, Webb is forcing us to face a quiet, undeniable truth. The framework of the early universe looks too neat, too polished, as if someone skipped the messy parts of construction. Take the Sears galaxies Webb captured. Smooth, rotational, structured, glowing in the darkness like finished cities that somehow appeared before the foundations were laid. And that's the real tension here. Dark matter halos weren't supposed to look like that. Not so early. Not so organized. Not without chaos leading the way. Mike Boylan Colchin put it bluntly. These structures seem too massive, too early. If they're real, they put our standard model under serious tension. Dark matter was the part of our model we trusted the most. The quiet, reliable backbone that made everything else work. But now, even that backbone is bending. And that brings us to the biggest patch ever added to cosmology. A fix meant to solve every early universe problem at once. Inflation. Before we go any further, let's slow the universe down. Let's breathe. Imagine the cosmos when it was less than a trillionth of a second old. A tiny, trembling speck of energy, smaller than an atom, hotter than anything that has ever existed. And then, in a moment so brief, we can't even express it with normal time. The universe stretched. It didn't expand gently. It didn't grow like a balloon being inflated. It erupted outward, faster than the speed of light, faster than anything in nature today. A sudden, blistering, exponential growth. This event is what we call inflation. The cosmic miracle that once saved the Big Bang Theory from falling apart. Because inflation solved three huge problems that used to haunt cosmologists. First, the horizon problem. Why does the universe look the same everywhere, even in regions that never had time to communicate? Second, the flatness problem. Why is the geometry of the universe so perfectly balanced, not curved inward, not curved outward, but astonishingly flat? Third, the monopole problem. Why don't we see the exotic magnetic relics that certain early universe models predicted? Inflation fixed all of that in one elegant sweep. Think of the universe as a crumpled sheet of paper, wrinkled, irregular, chaotic. Inflation grabbed the corners and stretched it flat. When you stretch something enough, all the wrinkles disappear. It was beautiful, simple, powerful, and for decades, it worked. Inflation told us that the early universe should be relatively simple, tiny fluctuations, tiny ripples in density, just enough to seed galaxies later, but not enough to create complex structure right away. Cosmic dawn, under inflation, should have been gentle, quiet, slow. But then, Webb looked, and the early universe didn't behave like a flattened sheet at all. It behaved like a landscape full of cliffs and mountains, galaxies too large, too bright, too organized, too early, not just a few. A pattern inflation wasn't expecting. The density fluctuations that inflation predicts, the tiny seeds of future galaxies, don't match what Webb is showing us. Instead of small, gradual bumps, Webb is seeing huge early structures, far bigger than the initial conditions inflation allows. It's not that inflation is wrong. It's that the early universe looks more complex than the model was designed to handle. And then there's a deeper discomfort among cosmologists. Inflation, in many versions, leads to the idea of the multiverse, an endless branching of universes, each with slightly different laws of physics. Beautiful to imagine, impossible to test. A theory that predicts everything, predicts nothing. And that's where inflation begins to peel. Not because it's false, but because it might not be the whole story. Maybe inflation was only one phase among several. Maybe the early universe didn't behave linearly. Maybe space-time itself had quirks at high energies that we haven't yet discovered. You don't need to grasp every theory. You don't need equations or technical jargon. Just hold this image. Inflation once felt like the perfect solution, a golden key that unlocked the early universe. But perfect stories rarely survive perfect data. And Webb's data is not gentle. It is not forgiving. It is showing us an early universe that refuses to be simple, refuses to be smooth, refuses to be flattened into something predictable. Alan Guth, the father of inflation, once said, "Inflation was never meant to be the final word." And now, for the first time in decades, it feels like cosmology is listening. Because if inflation was supposed to make the early universe chaotic, messy, and rapidly smoothed out, then why does Webb's early universe look so remarkably calm, structured, and polished? Almost too polished. Before we dive into the wildest anomaly of all, let's pause for a moment, breathe in, and picture something simple. Imagine the universe as a newborn. You'd expect it to be messy, loud, chaotic, uncoordinated, a cosmic infant stumbling through its first steps. That's what cosmology predicted. The early universe should have been a place of collisions and distortions. Galaxies small, jagged, still assembling themselves. Stars forming in uneven patches. Cosmic filaments barely beginning to appear. A web of gravity just starting to tighten its threads. Everything should have looked rough, raw, unfinished. But then Webb opened its golden eye, and the picture was nothing like that. Instead of chaos, Webb saw calm. Instead of turbulence, Webb saw order. Instead of a universe still learning to walk, Webb found one already standing tall. Smooth disks, well-organized rotations, galaxies aligned in elegant shapes, cosmic filaments already stretching across space like scaffolding built long before schedule. This wasn't supposed to happen. Not that early. Not that fast. It's the kind of discovery that makes even seasoned astronomers exhale slowly and whisper, "That's strange." For listeners in their 40s and beyond, people who've watched technology evolve, systems grow, cities rise, here's an analogy you'll appreciate. It's like buying a brand new hard drive, plugging it in, and finding it already neatly organized into labeled folders and curated photo albums. No clutter, no raw files, just a suspiciously perfect system that seems to have skipped the messy setup process entirely. And that's exactly the problem. To become smooth, a galaxy needs time. It needs to rotate long enough to settle its stars into a disk. It needs to survive collisions and mergers that would twist its shape. It needs gravitational breathing room to stabilize. But the galaxies Webb is seeing are too young to have done any of that. They simply haven't lived long enough. So what could explain this cosmic neatness? Possibility 1. The early universe was so dense that gravity worked faster. Higher density could mean quicker collapse, faster settling, and more stable systems forming in record time. But even this doesn't fully match the smoothness Webb observes. Possibility 2. There's hidden physics that naturally drives order from chaos. Something in the early universe, perhaps tied to dark matter, gravity, or the behavior of space-time, might have encouraged rapid organization. A kind of cosmic autofocus, bringing clarity far sooner than expected. Beautiful to imagine, not yet understood. No matter the explanation, the outcome is the same. The earliest chapters of the universe look too tidy, suspiciously tidy, as if someone skipped ahead in the story and left out the messy parts. Erica Nelson, a leading researcher studying these early galaxies, summarized it bluntly. Everything is forming too early, too massive, too smooth. It's like the universe skipped the messy parts. Let that sit for a moment. The early universe, the one we expected to be full of noise and collisions and half-finished structures, looks more like a quiet cosmic afternoon than a chaotic cosmic dawn. The universe looks calm, beautifully calm, too calm. And if that feels unsettling, don't worry. The next discovery is even stranger, because coming up now is the anomaly that cosmologists reluctantly call the impossible galaxies. And if all of this sounds strange, wait until you meet the galaxies that cosmologists now call impossible. Astronomers don't use dramatic language lightly. So when they start saying a new phrase out loud, sometimes with a sigh, sometimes with nervous laughter, you know something unusual is happening. And that phrase is impossible galaxies. Not because they defy physics, not because they break the laws of nature, but because, under our current model of the universe, these galaxies simply shouldn't exist. They violate the schedule. They outgrow their timeline. They jump ahead in cosmic evolution before the script says they're allowed to. Let's take a closer look at what makes them impossible. 1. They are incredibly far away. Their redshifts place them close to the cosmic dawn, a universe only a few 100 million years old. 2. They are astonishingly bright, brighter than galaxies that should form billions of years later. 3. They are extremely massive, hundreds of billions of stars worth of material, packed into systems that should barely exist yet. 4. They are metal-rich, which implies many generations of stars lived and died long before they were supposed to. 5. They are orderly, smooth disks, recognizable structure, rotation patterns that require time the early universe simply didn't have. Taken together, these traits form a category so strange that cosmologists reluctantly gave it a name: the impossible galaxies. A story from Webb's early days. Let's tell it like a small space thriller, a quiet one, the kind that still lets you relax. Webb was observing a deep field, peering into a patch of sky that to the naked eye looked empty. But in that darkness, it found something odd. A galaxy glowing brighter than the models allowed, with colors suggesting a redshift so high that astronomers initially thought, this must be a mistake. Maybe it was a photometric redshift error. Maybe lensing made it look brighter. Maybe it was a noisy data point pretending to be something extreme. But then came spectroscopy, the gold standard, the cosmic lie detector. The results confirmed it. This galaxy was exactly as far, exactly as bright, and exactly as massive as it first appeared. It was real. No errors, no illusions, no easy explanation. And suddenly scientists found themselves staring at a problem they could no longer wave away. Why are they impossible? Under LCDM and the 13.8 billion year timeline, there isn't enough time to gather that much mass. There aren't enough star death cycles to enrich the gas with metals. Structure shouldn't have stabilized into disks yet. Black holes shouldn't have matured. dark matter halos shouldn't be that developed. It's like going to the first day of kindergarten and finding a room full of adults in business suits complaining about their mortgages. Or better yet, an analogy that hits even harder. It's like checking your bank account and finding $1 million you were never paid. And then the bank confirms the balance is real. No glitch, no misunderstanding. Just reality refusing to match the story you were told. At this point in the video, take a slow breath. Let the idea settle. Data doesn't apologize. Theories do. And Webb is delivering data that refuses to bend. What makes this even more powerful is that we're not talking about one or two strange galaxies. We're talking about a population, enough objects, found across multiple fields and independent teams, that the anomalies form a pattern. A pattern Webb keeps repeating. A pattern that cosmology cannot ignore. Mike Boylan Colchin said it plainly. If these galaxies are really as massive as they appear, then we're going to have to rewrite a lot of what we thought we knew about the early universe. When galaxies refuse to fit inside our timeline, it isn't the galaxies that are wrong. It's the timeline. And this leads us to the next question. 1. You might already be asking quietly to yourself as you drift deeper into this cosmic story. What do you do when there isn't enough time in the universe to build what you see? You either speed everything up, or you admit the clock might be wrong. Imagine this. It's your first day at a brand new job. You walk in expecting confusion. New faces, new tasks, new systems. But instead, people greet you by name. Your desk is already set up. Your calendar is full. Your email signature is formatted. Everyone seems to know you, as if you've been working there for years. You would stop and think, hold on, something happened before I arrived. That's exactly the feeling astronomers are facing right now. Because when Webb looks into the young universe, everything, galaxies, stars, black holes, dark matter halos, behaves as if it has a long, complicated backstory that simply doesn't fit inside the 13.8 billion year script we've written. It feels preloaded, as if cosmic history started earlier than the Big Bang timeline allows. Let's pause and gather the pieces. 1. Galaxies. They are too big, too smooth, too organized, too early. The kind of systems that should require billions of years, yet they're there in the first few hundred million. 2. Stars. Multiple generations have already lived and died, sprinkling metals into the gas when there shouldn't have been enough time for even one full cycle. 3. Black holes. Supermassive giants, the size of the Milky Way's central engine, sitting in a universe that's barely out of its cosmic cradle. 4. Dark matter halos. Instead of being messy and turbulent, they appear stable, mature, as if someone fast-forwarded their formation. Put all of these together, and they whisper the same quiet message. There just isn't enough time. Not in the models, not in the timeline, not under the assumptions we've held for decades. And so cosmologists find themselves at a crossroads, facing two broad ways to interpret the problem. Branch 1, turbophysics. Maybe the early universe had mechanisms that allowed everything to form faster. Supercharged star formation, exotic gas dynamics, dark matter behaving in ways we haven't modeled yet. In this view, the universe isn't older. It just worked in hyperspeed mode during its first moments. Branch 2. The timeline itself is incomplete. Maybe we're the ones who are early. Maybe the universe is older than we think. Maybe the Big Bang wasn't the absolute beginning, but a transition, a chapter break in a much longer cosmic story. This idea isn't saying the universe cheated. It isn't denying the Big Bang. It's simply suggesting that the story we've been told might not be the whole story. Here's a softer image for you. Something easy to carry as you drift into thought. It's like buying a brand new computer, turning it on, and discovering thousands of files, bookmarks, and browsing history already on the drive. Someone used this machine before you. Something happened before page 1. And for the universe, Webb is hinting at exactly that. George Ellis, one of the deepest thinkers in cosmology, captured the sentiment perfectly. Our models are stories we tell about the data. Sometimes the data quietly asks for a different story. So if the universe looks preloaded, if its earliest chapters feel more like a sequel than a prologue, we have to ask the next natural question. Did we mistake cosmic noon for cosmic dawn? We call it cosmic dawn, the first light after a long dark night, a poetic moment, a universe opening its eyes. But what if the light Webb is showing us isn't morning light at all? What if it's something closer to noon? Because when Webb stares deep into the past, the universe doesn't look like a newborn. It looks busy, awake, already in motion. Galaxies aren't fumbling through their first steps. They're rotating in organized disks. Black holes aren't seedlings. They're already devouring matter like seasoned giants. Stars aren't forming in their first generation. They're living, dying, enriching the cosmos, leaving behind chemical fingerprints of multiple cycles. That isn't the silence of dawn. That's the hum of midday. Here's an image for you. One that might feel familiar if you've ever left the house early. You walk outside thinking it's sunrise, expecting quiet streets and empty sidewalks. But instead, you find the sun already high overhead. Traffic roaring, coffee shops buzzing, the world fully awake. And you think, wait, did I wake up late? Or did the day start earlier than I realized? That is the question astronomers are now asking of the universe. If what we call cosmic dawn looks more like cosmic noon, then maybe we're not witnessing the beginning of everything. Maybe we're witnessing the beginning of a new cycle within something older, larger, deeper. Because cosmology, even at its most careful, allows room for possibilities that stretch far beyond a single, one-time beginning. Some models imagine a universe that expands, slows, contracts, and then bounces, giving rise to a new expansion phase, a cosmic heartbeat repeating over unimaginable timescales. Others suggest multiple phases of expansion, each with its own Big Bang, nested inside a grander cosmic history. These ideas are not declared truths. They are whispers, concepts sitting at the edges of theory, waiting for data strong enough to bring them into the center. And you don't need to choose between them. You don't have to decide anything. Just hold the possibility, gently, that what we call the beginning might simply be a chapter break rather than page 1. A moment in a much longer book. Take a breath. Let your mind drift. You're not being asked to adopt a new model. You're being invited to consider that dawn is a matter of perspective, that maybe the universe had a long morning before we arrived. one that the Big Bang didn't fully erase. Roger Penrose once expressed this feeling in his own way. The universe may not have a single beginning, but a series of aeons, each giving birth to the next. And perhaps, just perhaps, Webb is giving us the faintest hints of a previous aeon bleeding into this one. So if cosmic dawn feels too mature, too active, too awake, maybe it's because we didn't catch the universe at sunrise. Maybe we woke up in the middle of a very long day, before the Big Bang became the king of modern cosmology, before textbooks embraced it, before it became the story most of us grew up with. There were other ideas on the table. Ideas that didn't like the notion of a beginning. Ideas from scientists who looked at the night sky and felt that an eternal universe, one with no birth date, was more elegant, more satisfying, more logical. Let's drift back for a moment into the middle of the 20th century. Imagine white chalk on a blackboard, coffee-stained notebooks, a generation of thinkers wrestling with the question, did the universe ever truly start? Back then, 3 names shaped an alternative vision: Bondi, Gold, and Fred Hoyle. They proposed the steady-state model, a bold idea. In their picture, the universe expands, yes, but its density never changes. Because as galaxies drift apart, new matter continuously pops into existence from the vacuum, filling the gaps like water rising to match an overflowing cup. To them, the universe was eternal. No beginning, no end, no dawn or dusk, just a cosmos that always looked more or less the same, in every direction, at every time. It was elegant, philosophically appealing, beautiful even. But in 1965, something happened. 2 radio engineers detected a faint microwave glow, the afterlight of a hotter, denser past. We call it the cosmic microwave background. And with that discovery, the Big Bang quietly won the debate. Steady state faded into the background, an idea retired, archived, shelved. But science rarely forgets completely. Ideas tend to drift back into the conversation when new data shifts the ground. And with Webb showing a universe that seems preloaded, with complexity arriving too soon, some scientists have opened those old books again, not to resurrect them, but to reconsider certain pages. Because after steady state faded, a new family of ideas emerged: quasi-steady models, cyclic universes, bounce cosmologies, not claiming a single beginning, but a universe passing through repeated phases: expand, slow, crunch, bounce, expand again. Each phase with its own bang, its own chapter break, its own version of cosmic dawn. No single creation moment, but a long chain of aeons, each giving birth to the next. Webb isn't proving any of these models correct, not even close. But the fact that the early universe looks so mature, so structured, so bright, so chemically rich, has nudged some cosmologists to wonder, if this chapter looks like noon, maybe the book is older than we thought. You don't have to buy into any of these ideas. You don't have to pick a side. You're simply being invited to imagine a broader landscape, a cosmology where Big Bang may be correct and still not be the whole story. It's like pulling an old volume off the shelf, one you once dismissed, only to find that a single paragraph suddenly feels relevant again. A reminder that science is not a static monument, but a river that bends when new terrain appears. Fred Hoyle, ironically, one of the fiercest opponents of the Big Bang, captured the sentiment perfectly. Science is not about consensus. It's about what stands when the data stops changing. And Webb's data is changing things. So now, as we stand between old ideas and new light, there's one more perspective worth exploring. One that doesn't build the universe from gravity and expansion alone, but from something even more fundamental: electricity and plasma. Before we land this journey, there's one more lens worth visiting. Not to endorse it, not to argue for it, but simply because it adds texture to the landscape of ideas. A reminder that humans have always tried to make sense of the same sky in many different ways. Let's start gently. Most of the matter we can see in the universe, the kind that glows, burns, shines, isn't solid or liquid or even ordinary gas. It's plasma, ionized gas, charged particles, matter that responds to magnetic fields as easily as it responds to gravity. Stars are plasma. Nebulae are plasma. Even the thin threads of material between galaxies drift in this strange electrified state, and that observation inspired a fringe, but fascinating idea: plasma cosmology. In this picture, the universe is not shaped primarily by gravity, but by electromagnetic forces. Forces far stronger than gravity, capable of sculpting vast filaments, knots, and webs stretching across cosmic distances. Imagine the cosmic web not as a network woven by dark matter and gravity, but as an enormous electrical grid, currents flowing across millions of light years, twisting magnetic ropes, pulling plasma into threads that glow faintly in the darkness. It's a dramatic vision, a bold one, and for some, a deeply compelling one. Plasma cosmology suggests cosmic filaments are giant current-carrying structures. Galaxies might form in magnetic pinch points. Electromagnetic forces play a major role in shaping structure. It's imaginative. It makes certain patterns feel intuitive. And it resonates with anyone who sees the universe as dynamic, alive, charged. But like any idea, it comes with weaknesses. Plasma cosmology struggles to explain the cosmic microwave background, the abundance of light elements, and the precise expansion history confirmed by multiple probes. It paints a beautiful picture, but it doesn't fit all the data we have. Still, Webb has added some intrigue, because when Webb captured early cosmic filaments, sprawling structures that appear earlier than expected, a few scientists wondered whether plasma behavior might play a larger role than we've assumed. Not replacing gravity, not overthrowing dark matter, just adding another brushstroke to the cosmic canvas. Mainstream cosmology remains skeptical, as it should. But the idea doesn't fully disappear, because it reminds us that the universe is vast enough to entertain more than one way of being understood. Take a breath here. You don't need to believe in an electric universe. You don't need to add plasma cosmology to your worldview. Just appreciate the diversity of human imagination. How many stories we've written to explain the same tiny flickers of ancient light. Because in the end, gravity, dark matter, plasma, expansion, quantum fields, timelines, cycles, these are just tools in a toolbox. Ways of asking the universe who it is. And Webb hasn't forced us to pick one. It simply nudged us to open the toolbox again and check whether we've overlooked something. Hannes Alfvén, a pioneer of plasma physics, once said, "We should remember that the universe is not only stranger than we imagine, it is stranger than we can imagine." And maybe that is the gentlest truth Webb has offered so far, that the universe may be too rich for any single model, too layered for a single story, too mysterious for one theory to hold it. So after all these ideas, all these timelines, all these impossible galaxies, what are you supposed to do with this, lying here in the dark? Take one slow breath. Let your shoulders fall. Feel the bed beneath you. Feel the weight of your own body settling into the dark. You press play tonight just to unwind, just to close your eyes for a moment and let something bigger than your day-to-day worries carry you away. And in the last hour and a half, the universe has taken you very, very far from home. It's shown you beginnings older than beginnings, galaxies that shouldn't exist, stars that lived too fast, black holes born before the timeline allowed, and models that once seemed solid now bending under new light. But before all of that, before redshift, before cosmic dawn, before Webb's mirrors unfolded, there was simply a person lying down, hoping the night might feel a little softer. Let's return to that person now. To you. Take another breath. Let the science fade into background hum. We don't need the equations anymore. Tonight we're not here to solve the universe. We're here to rest inside it. If you let your mind drift back across the story, you'll remember how it began. The Big Bang. A simple, elegant tale of a universe expanding from a point. Webb, a machine that can look backward through time. Impossible galaxies. Massive, metal-rich, structured too soon. Old stars in a young cosmos. Black holes that grew too quickly. Smoothness where chaos should have ruled. Models that stretched from inflation to steady state to plasma webs. Not to overwhelm you, but simply to remind you, the universe isn't wrong. It's just bigger than the stories we tell about it. Nothing shattered tonight. No alarm bells, no cosmic disaster. Just a gentle nudge from the cosmos saying, your map needs updating. No rush. We're not watching the universe fall apart. We're just watching cartographers redraw the map. And you don't need to hold the pen. Not tonight. Think of your life for a moment. Tomorrow will still come with its usual rhythm. Emails, commutes, decisions, the weight of being human. The earth will still turn. The sun will still rise. Your home, your routine, your people, all of it stays. No matter what Webb sees or what timeline shifts or which theory wins the next round, your world remains steady. Let that thought soften you. Feel your breath move in and out slowly. Let your chest rise and fall in the dim quiet of your room. The universe is enormous, but your space, right now, is small and safe. Let it feel that way. Close your eyes if they aren't closed already. Let everything you learn tonight drift outward, like galaxies moving apart in the dark. The strange objects, the impossible timelines, the models arguing with each other. Let them go. Let them float somewhere far outside your worry. You don't have to carry them. You don't have to carry anything right now. You've carried enough today. Work, responsibilities, family, finances, the silent weight every adult shoulders alone. You don't have to carry the universe's questions too. Let them drift. Let them become faint, distant starlight. All that matters now is the gentle weight of your body, the softness of the pillow beneath your head, the quiet dark holding you like a blanket. There is beauty in not knowing, in letting mystery exist without demanding answers. You were born in a time when our cosmic story is still being rewritten, a front row seat to the universe updating itself. What a privilege to listen, to wonder, to rest inside the questions, and also, what a relief to know you don't have to solve any of them. Not tonight, not tomorrow, maybe not ever. So exhale. Let your mind loosen its grip. You are safe. The earth is steady beneath you. Above you, the universe is still arguing with itself in equations and photons and ancient light. But it's in no hurry. You don't need to solve any of it. Let the galaxies drift back into the dark. Let the questions fade to the edges of your mind. You are safe. The universe is quiet tonight. You are safe. The universe is quiet tonight. And if sleep reaches for you now, just let it. Good night, traveler.